This lesson is on degrees and radians. This is section 4.2 from your book. So angles are defined as two rays that share a common vertex. What does that mean? So we have two rays, a ray like this maybe, and a ray like this, and we're saying that the vertex in between here is what they share, and this causes this angle. So we call that an angle when we have two rays that share a common vertex. We can also think about an angle as being formed by rotating a ray about its vertex or its end point. So the idea of that is you start with a ray here and you rotate this ray until you get to a certain point, and then whenever you stop, that creates your angle. So the initial side is that starting place. That's along the positive x-axis if we are in standard position. So standard position, this starting place where we started for our angle, that is our initial side, and it's said to be in standard position if it's along the positive x-axis. Where we finish, that place that we end that causes our angle to be created is called the terminal side. So we have the initial side and the terminal side. The terminal side is our final position. Final position. So here are some pictures that have some examples. You can see this angle, initial side. The initial side is along the positive x-axis, which is therefore we call that standard position. And then we have some terminal side. A vertex is the place where they join, and this causes some angle. Angle in standard position. Our terminal side in this one is somewhere else a little bit farther. We can rotate. So far, the only rotations we've seen are in the positive direction. So we are moving counterclockwise. That is called positive rotation or positive angle. So this angle down here, we move, it's in the counterclockwise rotation. A negative angle is when instead of going to that positive y first and then that negative x and then that negative y, you hit the negative y first. So you're going in the clockwise rotation. That could create the same angle. So this angle, we could call that, I don't know, let's say it's 120 or something in the positive direction. So if we were counting in the clockwise direction, in the counterclockwise direction, in the positive direction, maybe this angle is 120. Well, in the negative direction, then it would be whatever 360 minus 120 is, which would be 240. But we have a negative angle, right? So it's in the negative direction. So I guess you could think about it as 120 minus 360. Maybe that's a better way to think about it. But you can see we get to the same point with those two different. We have negative 240 gets us to the same place as positive 120. Those angles are different though. The resultant vector is in the same location. So there are two ways that we commonly describe angles. We can describe them using degrees, which is what I just did above, or radians, which we'll talk about later. So degrees, most of you hopefully are familiar with degrees. You know that there are 360 degrees in one full rotation, which means that degrees, 1 degree is therefore equal to 1/360th of a full clockwise rotation. You may not remember that, but you know that there are 360 degrees in one full rotation, so therefore 1 degree is equal to 1/360 of a full clockwise rotation. That makes sense. So 360 degrees is equal to 1 rotation. We said that. 270 degrees is therefore equal to 3/4 of a rotation. That brings us here. 180 is equal to 1/2. 90 degrees is equal to 1/4. We could analyze more. We could say 45 degrees is equal to 1/8 of a rotation, and so on and so forth. An equivalent way to describe, so sometimes we don't have degrees that are full whole numbers. Sometimes we have them in decimal form. And so when we have them in decimal form, we can express them in decimal degree form or in degree minute second form. So these are equivalent ways of representing the same information. It's like saying I did something for an hour or I did something for 60 minutes. Those are equivalent things to say, and we can express them in those same ways. So the decimal portion of the degree, if we're trying to convert from decimal to minute to degree minute second, which is abbreviated as DMS, then the decimal portion of the original degree is multiplied by 60 to get the minutes, and then the decimal portion of that result is multiplied by 60 to get the seconds. So it's the same rules, the same numbers that you're used to. So let's do an example together. Convert from decimal degree form to DMS form, or from DMS form to decimal degree form, depending on what you're given. So we start with example A, 56.735 degrees. So the first thing we're going to do is we're going to take that 56 out. That's our whole number. We're going to leave that alone. And we're going to say 56 degrees plus 0.735 times 60. That's the very first thing we're supposed to do. The decimal portion of the original degree is multiplied by 60 to get the minutes. So then we have 56 plus 44.1 minutes. And then we're going to take the decimal portion of that and multiply it by 60 in order to get the seconds. So then you take the 56 degrees plus essentially 44 minutes plus 0.1 times 60, and you end up with 56 plus 44 plus 6. And the way that you write this is 56 degrees, 44 with just an apostrophe, and then 66 with like quotations or a double apostrophe. That represents 56 degrees, 44 minutes, 6 seconds. Degree, minute, seconds. Okay, let's go the other way. If we start with the degree, minute, seconds, we start with 32 degrees, 5 minutes, 28 seconds, and we want to convert back. Well, essentially, the seconds we ended up multiplying by 3,600, right? We did it twice, so we multiplied the seconds that way. So we're going to undo that part this way. So you take 32 out by itself. That's our whole number. We'll leave that alone for now. Then we take the 5 minutes, and we're going to divide that by 60 minutes, because that's in 1 degree. We have that many. And then 28, we're going to divide by 3,600, because that's how many seconds there are in 1 degree. We want to convert everything back to just standard degrees. We get 32 degrees plus 0.083 degrees plus 0.008, and that leaves us with 32.091 degrees. That's your final answer. So the first way we described angles was with degrees. That's what we just talked about, degrees. 1 degree is 1/360th of a full rotation. We can also describe angles with radians. Another way to describe the same information. So for a given angle, theta, radians, which are often measured in rads, you can just write it as rads, sometimes you can write it as radians. These are defined as the measure of length of the circumference divided by the radius. So what we're talking about there is we have some circle, we have some theta over here, right? We're saying whatever this length is, whatever part of the circumference, whatever that distance is, divided by this radius that causes this, that is equal to our theta in radians. So for larger angles, a larger part of the circumference would be selected, right? If we had an example where our theta was like this, and we're talking about this whole thing being our theta, then it's still that R, and this is our S. And we call that S our intercepted arc, or our arc length. Intercepted arc, or arc length. So circumference, we know the equation for circumference is just equal to 2 pi r, and radius equals r. So if we were talking about the whole circle, if we were talking about 360 degrees, we would have 2 pi r divided by r, and that would leave us with 2 pi radians. So if we're talking about a whole circle, we have 360 degrees, or equivalently, we have 2 pi radians. So that's for 1 rotation, we have 2 pi rad. For a half of a rotation, obviously we would have half of whatever the full rotation is, which is pi rad. But you could also do that instead of it being 2 pi r, this is just pi r divided by r. For a 4th rotation, again, we have whatever half of the half was, which is pi over 2. For a 6th rotation, we have pi over 3. You could go even further and say 45 degrees is equal to pi over 4 radians. This is a an angle measure. So we're talking about an angle measure when we're talking about radians. So more generally, we can simplify this to 1 degree is equivalent to pi over 180 radians, and 1 radian is equal to 180 degrees over pi. If you forget these, just to go back and do the math, you know that there's 360 degrees, you know circumference is 2 pi r, you know we're saying 2 pi r divided by r. You're going to get 2 pi is equal to 360. You can solve 2 pi rad is equal to 360 degrees, and you can solve that in order to get 1 degree or 1 radian. Okay, let's talk about coterminal angles. So coterminal angles are that's the vocabulary word to describe what we talked about before. When we end up in the same position, but we either went positive or negative, and we end up in that same position. So we can also do that rotation multiple times. Let's fill this in. So we discussed how two angles could have the same initial and terminal side, but different angle measures when they are rotated either positively or negatively. That's the example we did at the beginning. So the same can be said if they are rotated positively or negatively multiple times. So if we go around that circle more than once, we're getting a larger angle. You don't just say, but the resultant is going to be an equivalent. We call those coterminal angles. So angles of different measure that have the same initial and terminal sides. So they have a different measure. The angle is a different measure, but we have the same initial and terminal sides. These are called coterminal angles. And because we know that 360 degrees is 1 full rotation, or 2 pi radians is 1 full rotation, that's going to help us solve for when we have coterminal angles. So if we have this alpha is the degree of measure of an angle, then all angles measuring alpha plus 360 degrees times some n. So n could be -1. That's saying we're going wherever that angle was, and then a full rotation backwards, or n could be +2, and that means we are starting at whatever that angle was, and we are going a full 2 rotations in the positive directions. Where we're going to result in the same place, we're going to end up in the same original location, then we call that a coterminal angle. The same thing can be done with radians. So if you start with some angle alpha and you add 2 pi n to that, n is an integer, then whatever angle you are resulting in, that's coterminal to the original angle. It's not equal, it's coterminal. So let's do an example. Identify all angles that are coterminal with a given angle. So we're given 45 degrees, which means all the angles measuring that are going to be coterminal are 45 degrees plus 360 times n degrees. So that's your answer. And you could do a couple examples. You could plug in n equals 1. You could plug in n equals -1. If we plug in n equals 1, you see we start with this 45, and then we go around an entire other rotation, and we end up in the same location. So if we did -1, it's very similar, except we start at 45, and we go a full rotation backwards, 360 degrees. We can do the same for this other example with radians. So if we're given, instead of 45 degrees, if we're given -pi/3, and we're asked to find all coterminal angles, this is going to mean that all coterminal angles are equal to -pi/3 plus 2 pi n. So n is any integer, and we're going to do the same thing. So you could plug in, again, 1 or -1 as examples. Those are not the only available options. So if theta is a central angle in a circle, let's talk about some arc length. We talked about that briefly before. It's that s, it's that distance around that circumference. Then the length of the intercepted arc is given by s equals r theta. This is the same thing we did before, right? We said theta equals s over r. We're just rewriting the equation to solve for s. So if we're trying to find arc length, then s equals theta times r, or r theta. And again, theta is measured in radians in this example, because that's how we're finding radians. So let's do an example together. We said find the length of the intercepted arc in each circle with the given central angle, measure, and radius. Round to the nearest tenth. So we start with pi/4, and we have r equals 5 centimeters. So s is equal to r times theta. Therefore, this is pretty easy. I hope you guys know how to do this. S equals 5 times pi/4, right? We're just filling in the stuff we know. Therefore, s equals 5 pi/4. If you wanted to convert that, which you should get about 3.9 centimeters in your calculator. 5 times pi divided by 4. We started with centimeters. Let's leave it in centimeters. We end up with this arc length equal to 3.9 centimeters. So that's this length right here equals 3.9 centimeters.